All right, folks, I'm going to go ahead and warn you now. Brace yourself because it's coming. So, for those of you who hate Excel, this is the other option that you have for Standard Edition. For those of you who hate Excel, and after you see this example problem, you might love Excel after this. That might be your new best friend. But I'm going to go through a way that we can solve Standard Editions algebraically. All right? We're not going to do it graphically. We're not going to do it with Excel, but we're going to do it by full-blown equation. So I hope that you got your notepads ready. I hope that you got your calculators ready. I hope you got your fingers cracked, your knuckles stretched, and your pen ready to burn, because this is going to be heavily math. So bear with me. In the process of Standard Addition, let's think about what we've done. We've made a set of standards. One of them was a blank, which was just my sample, and that was it. And then the standards that I've made was a sample with a little bit of standard that I have added into it. And this is a known concentration. I know the concentration from the beginning, and I know how much I've added. Well, let's say I'm not going to do this with Excel. I'm not going to plot any curve. I have to go into this with the understanding that if I put more and more standard, then this is proportionate to more and more signal. And it's directly proportionate. The more I add, the more it goes up. So I have to assume that that ratio exists. So let's quickly turn to maybe something a little more realistic. And that way we can talk and discuss about this process of the equation in more detail as we go. So here's the example problem. Let's imagine for a minute that we have a sample that was brought to a lab. And this sample was measured for sodium content. So they could have used multiple different tools or technology or instruments for this. And let's say that we use maybe some type of probe, and we get millivolt as a signal from the instrument. Remember, I said absorbances are common, but we're just going to generalize it to signal, and this is one of those units that we could see. So let's say that this sample that was brought into the lab had a signal of 4.27 millivolt. This was the same as we saw in the previous problems. This was a sample given to the lab. We analyzed it. We saw it had a signal because we knew stuff was present already, and we plotted it on an Excel graph. And at the 0 mark, it was way above the 0 on the y-axis, and that's where this linear regression line started. And that was why this sample had stuff in it. Well, in the next set, we kept saying, well, I'm going to take some of my sample, and I'm going to add some standard to it. I'm going to dilute it to the line, and then we're going to rerun it. And we're going to see what kind of signal we get with that. Well, that's what's going to happen here. So after the sample was brought in, we then took 95 milliliters of that sample. We added 5 milliliters of sodium standard to it, and we reran it. Well, this standard, I need to know the concentration for it. That's 2.08 molarity. And when I run this setup, this spiked or this standard addition, I get a new signal. And that signal is 7.98. This is all we do. Let's say we're not even going to bother with more standards. This was it. We're lazy. We're having a bad day. We just want a general idea of how much is there. Maybe we don't need to be completely accurate. So we just make one. That's all we do. And we run it. Well, if I look at this signal has went up, right? This signal has increased to there. And depending on how much this goes up, well, the concentration should go up as well in the same amount. That's the whole idea of standard addition. So now I need to figure out, how do I handle these numbers? Is there a way that I can solve for this unknown concentration that was brought to me without a graph, without Excel, just based on these two measurements only? And the answer is yeah. It's going to take a little bit of effort. It's going to take a little bit of math, some equation talking. We're going to get through it. We're going to do that example. And maybe you'll like this method a little bit better. So let's keep this in mind. Sample was delivered to the lab. We ran it. Then we took that sample, put about 95 milliliters into a volumetric flask. We added 5 milliliters of this stuff, which was my sodium standard, that was the strength, to that flask. And then we reran it. And we got a new signal. So what's the next step? Well, I need to introduce you to an equation. And this is what the equation is going to look like. I have an unknown. Don't really know what that is, concentration-wise. And this is the unknown that was brought to me from the very beginning. So we're going to use I for initial. Well, that unknown we can run and we can get a signal for it. The way that we put in the signal is I for the instrument. I represents the instrumentation that was used. This is the signal from the piece of equipment. And this is the signal from the unknown. I don't know how much is there. Well, each side of this is going to be divided by something. But at least the top part goes together, right? This is the sample that was given. I don't know how much is present. This is the signal of the sample that I didn't know how much was present. On the bottom, what happens is that we have now taken a little bit of standard. In all of these examples, we've taken some standard. And we have added it to the sample and brought it to a volume, a final volume. So S sub F is what that stands for. That is my standard. I've added a little bit to it, and I've diluted it to the line. So final volume. Well, in that flask, there is also the unknown amount that was there from the very beginning. And the same thing's happening there, right? I've added this solution to a volumetric flask. I've added a little bit of standard, and then I've diluted on up to the line. That gets weakened down too. So I've got to put an F there as well. So in this problem, we've taken 5 milliliters of sodium standard. We took it to a final volume of 100. And then we took our sample, 95 milliliters, and we took it to a volume of 100 in total. Both of these get slightly diluted. All right, well, over here on this side, what goes with that? Well, it's another instrumentation signal, right? We made this setup, this combo, and we ran that combo in the instrument, and we get a signal from that. So the way that I represent that is I do X plus S, right? This is the instrument signal from just the sample, and this is the instrument signal from the sample and the standard that was given. There's the setup, ladies and gentlemen. That's the math that we will begin with in order to solve this problem. Now, some of these are very simple to start to fill in. In almost every single case, in almost every one of them, this top value, this x sub I, this is what we're looking for. That is the concentration of the unknown in the very beginning when it was brought to me. That's really what standard addition is all about, trying to discover how much is present. So almost every single time, that top one will always be the variable that you're trying to solve for. Well, in this case, we know that we're looking at sodium. So what I'll do is I'll just put bracket sodium there just to kind of, make this all cohesive a little bit. And we know that we are looking for the initial concentration of sodium in the sample. That's all that I've done. Well, I know that when I ran that sample on its own, I got a signal from that. And like we said before, just a minute or two ago, that sample gave me an analysis of 4.27 millivolt. So that's the signal from the machine. That's the number that I'll plug there into that equation. Well, it looks like we're halfway done, right? That's not too bad. Hopefully that kind of makes sense, right? I take my unknown, I run it. Whatever that signal is, that's what goes over there. Hey, makes kind of sense. Well, this instrumentation signal of the sample plus the standard that I've added, this is another easy number for me to get because that was the signal after I added my stuff to it. Well, in the previous example, or the one that we just talked about a couple of minutes ago, 7.98 was that signal. After we added more sodium to the sample, we reran it, and that rerun that had more sodium in it ran higher, and it should, and that was 7.98. Well, so far, everything looks okay. I thought he was telling me this was going to be bad. Well, it's the next step that gets a little tricky for people. So we're going to take our time, and we're going to talk about each one of these. And I'm going to start with the easiest one first, and that's the SF. So the SF, the S stands for standard, right? And this represents the standard final concentration. So the final concentration of the standard, that's what that number represents. Well, this should not be a problem for you. You just got to kind of think about what's happened here. Go back and take a look at the problem that we described. What we said is that we took 5 milliliters of a sodium standard that was, 2.08 molarity. And we added that to 95 milliliters of sample. Okay, so one of the biggest problems here is the wording of the problem. If you've taken 5 mils and added it to 95, that's going to give you a total of 100 mils. That's what a lot of people forget to do here. Just think about it in terms of a volumetric flask. You had 95 mils of sample in a container. You added 5 mils to it. Well, that brings it up to 100, right? To me, it kind of makes common sense, but to other people, they don't really put it together that way because, quite honestly, they've not had the experiences that you have had in a laboratory. So if I take 5 mils, add it to 95, I get a total of 100. Well, this S sub F, the final concentration of the standard, I can solve for that, because the only thing that I need is the dilution equation. So I'm coming over to the side and I'm doing this side calculation to get a number so I can plug into the main standard addition equation. Well, you do this just like before. We've done dilution over and over and over. Don't let this throw you off. So the molarity of the stuff that I've used is 2.08, and the direction said that I have used 5 milliliters of that. So I want to know what is the final concentration if I took this to 100 mils in total. That's all that we're doing here. That's all that that bracket S sub F means. That's it. All right, so I'm going to bring my calculator over to the side so you can watch me key this in. 2.08 times 5, because we used 5 mils of it. And then we're going to divide by 100. And that gives me X. And X is the concentration of the standard that I have added. We did this same thing when we did it graphically. There's no difference, right? We knew we added a certain amount of standard. We knew the concentration of it. We did a dilution to figure out how much was present concentration-wise after that whole mess took place. And that's the number that we plotted on the X-axis in Excel. No difference at this point. No new information has been presented. So 0.104 is the answer. And that is the concentration that I would have plotted on an Excel curve. Well, that's what this bracket S sub F represents here. Final concentration of the standard. I just solved for it. 0.104. So I'm going to rewrite this because remember this X represents what you're looking for, and in this case we're looking for sodium, so there's a bracket around sodium there, but this is the final concentration of sodium. So it's this piece that we have a question about. That might be the new piece of information that we really haven't discussed as far as the graphical side to solve these problems go. So we're going to have to learn how to manipulate that variable. I can't solve an equation with two variables very easily. But if I could switch that variable to something else, then maybe I could do funny things with the math and the equation setup, and I can get an answer. So this is where I'm going to stop this video for now. All of this is just kind of a summary of what we've already done, right? We're looking for the concentration of the original sample. So this is in red, that is the answer that we're after. That's what we want to solve for. Well, that sample was ran and gave me a 4.27 signal. I then made another. I took some sample. I added it a little bit of standard. I reran it, 7.98. This equation tells me, hey, you need to figure out what the final concentration of your standard was. You added it in there. You should be able to figure out how much you've added. And that's what we did in purple over to the right-hand side of the screen. We did the molarity equation or dilution equation, 2.08 times 5 because we used 5 mils of that standard, and then we diluted it to a total of 100 mils. That gave me a concentration of 0.104, and that's what went into bracket S sub F. So come back in the next video. I'm going to pick up from here. We're going to talk more detail about this bracket F, and we're going to talk to you, or I'm going to talk to you, unless I've got multiple personality disorder, which maybe sometimes I question it, but I'm going to talk to you about how to manipulate this so this equation becomes much simpler to solve.